Solution of a state equation. In this exercise, we consider first a continuous time linear system. Then after, we'll treat the discrete time case. So we start with a continuous time linear system, and we have to find this expression for the solution. The first part of this solution is called homogeneous, or free, or transient solution. And the second part is called force because of u, and here free because of the initial condition. I consider x dot equal ax plus bu. All depend on t. I will define z of t, which is equal to exponential minus at x of t. So we have also, due to the fact that this matrix is invertible, I will have x of t equal at multiplied by z of t. So how can I check this? It is first, if I multiply these two matrices, multiply by at. Because these two matrices are commutable, so they can commute. So what that means? It means if I take the matrix at, and if I multiply by minus at, it is the same as minus at multiplied by at. So I can commute them. In this case, I know that this is equal to the exponential of minus at plus at, which is equal to exponential of 0, which is equal to the identity. Okay, so I have this first. I consider this one, and I will replace by taking this into account. So x dot. From this, I got I will differentiate this, and I obtained that a exponential at, so the derivative of this, multiplied by z of t, plus exponential at multiplied by z dot of t is equal, so I take this, x, so x is equal to exponential at z of t, and plus b u of t. Of course, I have some simplification. I have this and this, and then this one I know is inverse, though I can put it, I know that the inverse of this is exponential minus at, so I will be able to put here, and then as a result I get that z dot is equal to exponential minus at multiplied by bu of t. Okay, so from this, since I have no z on the right hand, I can integrate this relation and get that z of t is equal to z at time 0 plus integral from 0 to t of this expression of exponential minus at bu of, so I should put tau instead, tau d tau. Okay, so let me come back to x. So x, so that's x of t, which is equal to this exponential at times z. So I will have exponential at times z of t, where z is given here. So I will develop. It is equal to exponential at z at time 0 due to this, plus, so I will enter this term inside the integral. Because it does not depend on tau, I am allowed to do this. So I will have here integral from 0 to t, exponential at, exponential minus a tau, b u of tau d tau. Now at time 0, I have x due to this. X of 0 is equal to z0 because exponential a times 0 is equal to the identity. So this is equal to x of 0. As a consequence, I get that x of t is equal to this time x0 plus integral 0 and t of exponential a time t minus tau b u of tau d tau. So it means that the solution x is the sum of two terms, one who only depends on the initial condition and of the matrix A, so it does not depend on B, this one. So we understand that it is called homogeneous or free, whereas this one does not depend on the initial condition, but only on U and B. Of course, A is also involved. So this one is the fourth solution. So this separation is only for linear systems. And the stability, since there is no dependency when I am stable with respect to the initial condition, I can understand that only A is involved in the stability. Okay. Now I continue, and the second question here is I have to show, to find for the discrete time system, I have to find the solution in a similar way as I have done for the continuous case. So, second, I have a state equation of the form a at time k plus 1 is equal to a x of k plus b u of k, and now I have to show that the solution is x of k is equal to a power k x of 0 plus sum L equals 0 to k minus 1 a k minus L minus 1 b u of L. So we can understand that this corresponds to this corresponds to this, the integral here and the sum here are similar, so we can see some analogy between this formula and this formula. So to prove this, I will proceed by a recurrence. It will be a recurrence proof. So for this, since I have to prove this, I will check. It's quite easy for k equals 0. So for k equals 0, I can see that this will correspond to identity and obtain x0 equal x0. So it is okay. Now I have to show that if this formula is true for k, I have to check that it is also true for k plus 1. It is a principle of the proof by recurrence. So I will check this. A at time k plus 1 is equal to a x of k plus b u of k from this relation. Okay, So now I will take this formula and I will obtain that it is a times this, so it will be a k plus 1 x0 plus the sum L equal 0 to k minus 1 multiplied by a k minus L, so I don't have the minus 1 because I multiply by a, b u of L plus, also I have to add to this, plus b u of k. Now from this is equal to the sum from L equals 0 to k of a k minus L b u of L. So this corresponds to this formula for k plus 1. So the relation is therefore also verified for k plus 1. I have proved this formula. Again, I have the homogeneous solution, or free solution depending on the initial condition, and the fourth solution depending only on u.